Hello everyone, my name is Anushka and my roll number is 205015 and my topic is Sylow's theorem. So let's start. Sylow's theorem. Its statement. Suppose G is a finite group of order m and p is a prime number. If p to the power m divides order of G and p to the power m plus 1 is not a divisor of order of G, then G has a subgroup of order p to the power m. Now let's prove this theorem. So we'll prove this theorem by induction on order of G. So for this, we assume that the theorem is true for groups of order less than that of G. Now we shall show that it is true for G. To start the induction, we see that the theorem is obviously true if order of G is equal to 1. Let order of G is equal to p to the power m into n, where p is not a divisor of n. If m is equal to 0, the theorem is obviously true. If m is equal to 1, the theorem is true by Cauchy's theorem. So let m is greater than 1. Then G is a group of composite order, and so G must possess a subgroup H such that H is not equal to G. If P is not a divisor of order of G divided by order of H, then P to the power m divides order of H, because order of G is equal to P to the power m into n, which is equal to order of H into order of G upon order of H. Also, P to the power m plus 1 cannot be a divisor of order of H, because then P to the power m plus 1 will be a divisor of order of G, for which order of H is a divisor. Further, order of H is less than order of G. Therefore, by our induction hypothesis, the theorem is true for H. Therefore, H has a subgroup of order p to the power m, and this will also be a subgroup of G. So let us assume that for every subgroup H of G, where H is not equal to G, P is a divisor of order of G divided by order of H. Now consider this class equation. Order of G is equal to order of Z plus sigma A not belonging to Z, order of G upon order of NA. This we mark it as 1. Now since A does not belong to Z, this implies NA does not belong to G. Therefore, according to our assumption, P is a divisor of sigma order of G divided by order of NA. Also, P divides order of G. Therefore, from 1, we conclude that P is a divisor of order of Z. Then by Cauchy's theorem, Z has an element B of order P. Z is the center of G. Also, N is equal to the set B is a cyclic subgroup of Z of order P. Therefore, N is a cyclic subgroup of G of order P. Now, since P belongs to Z, therefore, N is a normal subgroup of G of order P. Now, consider the quotient group G dash is equal to G by N. So, we have order of G dash is equal to order of G divided by order of N, which is equal to P to the power M into N upon P is equal to P to the power M minus 1 into N. So, order of G dash is less than order of G. Also, P to the power M minus 1 divides order of G dash. But Pg is not a divisor of order of G dash. Therefore, by our induction hypothesis, M dash has a subgroup, say S dash, of order P to the power M minus 1. We know that the natural mapping psi such that G to G by N defined by psi x is equal to nx for every x belonging to G is a homomorphism of G onto G by N with kernel N. Let S is equal to the set x belonging to G such that psi x belongs to S dash. Then S is a subgroup of G and S dash is approximately equal to S by N. Therefore, order of S dash is equal to order of S by N, which is equal to order of S divided by order of N. Therefore, order of S is equal to order of S dash into order of n, which is equal to p to the power m minus 1 into p, which is equal to p to the power m. Thus, S is a subgroup of G of order p to the power m. This completes the proof of the theorem. Now let's move to a question. If H is a p-Sylow subgroup of G and X belongs to G, then X inverse Hx is also a p-Sylow subgroup of G. Suppose G is a finite group and order of G is equal to p to the power m into n, where p is a prime number and p is not a divisor of n. If H is a p-Sylow subgroup of G, then order of H is equal to p to the power m. Let X belonging to G be arbitrary, then X inverse Hx will be a p-Sylow subgroup of G if X inverse Hx is a subgroup of G and if order of X inverse Hx is equal to p to the power m. First, we shall prove that X inverse Hx is a subgroup of G. So let X inverse H1x and X inverse H2x be any two element of X inverse capital Hx, then H1 into H1 and H2 belongs to H. Also, we have x1 h1 x inverse h1x into x inverse h2x inverse is equal to x inverse h1x into x inverse h2 inverse x1 inverse to the power inverse, which is equal to x to the power minus 2 h1 e h2 inverse x, which is equal to x inverse h1 h2 inverse x, which belongs to x inverse capital Hx, since h1 h2 inverse belongs to H, as H is a subgroup of G. Therefore, x inverse Hx is a subgroup of G. Now let psi be a mapping from H into x inverse Hx, defined as psi H is equal to x inverse Hx for every H belonging to H. Now, to prove psi is onto, let x inverse Hx be any element of x inverse capital Hx, then H belongs to H. And we have psi H is equal to x inverse Hx. Therefore, psi is onto. Now, to prove psi is 1, 1, let h1, h2 belongs to capital H, then psi h1 is equal to psi h2 implies x inverse h1x is equal to x inverse h2x. X inverse and x will get cancelled by cancellation law, so h1 will be equal to h2. This implies that psi is 1, 1. Thus, psi is a 1-to-1 correspondence between the elements of H and the elements of x inverse Hx. Therefore, order of x inverse Hx is equal to order of H, which is equal to p to the power m. Therefore, x inverse Hx is a p-Sylow subgroup of G. That was the end of my presentation. Thank you for listening.